I would like to talk about rational functions again, and you can say, I'm fed up with them, I just saw 2. Yes, I just need one more to work on. So type 1, type 2, and type 3. Rational functions. What's all this? Nobody calls them type 1, type 2, and type 3. I just want to differentiate. Are there only 3 types of rational functions? No. But going beyond type 3, it's really excessive, in my opinion. So there's really no need to do that. We have seen type 1. Type 2, we can choose one. It's very simple, even easier than this one. This is type 1. Type 3 has a different story to tell. So type 1 is degree n over degree n. And we looked at 2 today. Degree 2 over degree 2 turned into degree 1 over degree 1. The one that we started at, we left off. We didn't finish last time, degree 1 over degree 1. So when the 2 degrees are the same, this function has a horizontal asymptote. It's normally the leading coefficient over the leading coefficient. So we saw here horizontal asymptote 1 and the previous one horizontal asymptote 2. This one is degree n, and this is degree greater than n. So bigger in the denominator. The only difference from type 1 is that the horizontal asymptote for type 2 will be much stronger in the denominator. Then the horizontal asymptote must be absolute. So let me write this one. It's not clear, Han? So this is greater than n. So if this is degree 3, this is degree 5 or 4 or 10, higher in the denominator.
Oh, and for the type 1, is it n?
Same.
Okay.
Same degree over same degree. This one, type 2, higher degree in the denominator. But this one is degree n, and this is degree n minus 1. So let me write it like this. 1 higher in the numerator, exactly 1. So degree 5 over degree 4, degree 3 over degree 2, degree 10 over degree 9.
It still could be more than that, right? So it could be like.
Yes, but that will not be type 3.
Right.
Yes, I can have degree 10 over degree 2, but it's not going to be any of these. Type 3
But
is
that would
only
still be 0, right?
Depending on the function.
Right.
Yeah, I have to look at it, which degree, how. But it will. What is the difference? These two have a horizontal asymptote. This one has a slant asymptote, either this way or this way. That's the only difference. If you change the degrees or the difference is not 1, the ratio or the quotient will not be aligned. So only when the degree of the top is by 1 unit higher than the degree of the denominator, that function has a horizontal has slant asymptote. No rational function has horizontal and slant at the same time. Doesn't exist. Okay, so I'd like us to look at a problem like this. Let's say f of x equals x squared minus 4 over x plus 1. Which category is it? Is it type 1, 2, or 3? I know it's a silly question. What is the degree at the top? The degree of the denominator?
1.
So which type is it? 1, 2, or 3?
3.
Of course. Right? The degree of the numerator is exactly by 1 unit higher than the degree of the denominator. We agree? Type 3. We know it immediately would not have a horizontal asymptote. It would have a slant asymptote. I don't know whether this way or this way. In other words, the end behavior will not be a number, but an infinity. That's all it means. So let's start with the domain. What is the domain of this function? X-intercept, Y-intercept. Yes, I will factor the numerator immediately. And you'll give me the domain. What is the domain? Okay. Anything but?
-1.
Very good. Negative infinity, -1, 0, infinity. Can anyone give us the x-intercepts? Very good. Do you all agree with -2 and 2? Because the numerator is 0. The numerator is 0 at 2 and -2. And please plug in 0. That's how we plug in 0. How much? Very good. I only need 1, 2, 3, 4 limits, and we're done with the function. So we want to find the limit as x approaches -infinity, the limit of as x approaches -1 left and right, and then x approaches infinity. So limit as x approaches -infinity from x squared minus 4 over x plus 1. Limit as x approaches infinity from x squared minus 4 over x plus 1. When we plug infinity in, what do we get? I always hope for infinity over infinity, or what is the other one? 0 over 0. Very good. So it is infinity over infinity in both cases. So then I can apply L'Hopital's rule. What do we get? When we differentiate the top, we get. When we differentiate the denominator, we get. Very good. And what is the answer? Very good. The last thing we need, left and right of 1. I'm sorry, left and right of -1. So limit as x approaches -1 to the left. So we know that x equals -1 is a VA. There is no discussion there. So x plus 2, x minus 2 over x plus 1. And limit as x approaches -1 from the right, x plus 2, x minus 2 over x plus 1. Okay, so -1 from the left means -1.1. This is positive. This is negative. This is negative. So 2 negatives. Good. -1 from the right, -0.9. This is positive. This is negative, but this is positive. So on the left, infinity. On the right, -infinity. We cannot find anything else about the function. Is this okay? Any questions, everyone? Okay, we're moving on to what? First derivative. So f prime of x, 2x at the top times x plus 1 minus x squared minus 4, everything divided by x plus 1 squared. The top function prime is 2x times the denominator minus the top times the denominator prime, which is 1. So remove parentheses, 2x squared plus 2x minus x squared and plus 4 over x plus 1 squared. So this is x squared plus 2x plus 4. Well, the numerator is not, can never be 0. Because negative b plus or minus the square root of 4 minus 4ac will be always positive. The denominator is always positive, critical numbers none. The function, the derivative is always positive, which makes the function always increasing. And now we'll see if that is true. From negative infinity to 0 to infinity, is that correct? From negative infinity to negative 4 to 0 to infinity, is that correct? Good. Indeed. It matches the sign of the first derivative. Now I have to work on the second derivative. Any questions? Okay. Ugly. Okay, the second derivative. Top function prime is 2x plus 2 times the denominator minus x squared plus 2x plus 4 times 2 times x plus 1 times the inner function prime. At this point, if you start distributing, you're never going to be able to finish. What is the key step now? Exactly. Factor and simplify. That's the key. And I see two terms, this term and this term. They have a common factor. I need to pull that out. Which common factor am I talking about? I agree. This. Very good. Awesome. Indeed. 2x plus 1. Perfect. Yes. 2x plus 2, 2x plus 2, or 2 times x plus 1. Excellent. I have to square x plus 1. How many terms I get when I square x plus 1? Yes. How many terms do I get?
3.
Yes, thank you very much. X squared plus 2x plus 1 minus x squared minus 2x minus 4. Without this key step, you're not going to be able to finish this. You understand that factoring is crucial here. And that's what we had in the previous chapter, right? We had those blah, blah, blah at the top and whatever in the denominator, and I was saying, please factor and simplify fully for this. Okay, now I can do this. Only now. Only when x plus 1 was taken out and it became a factor, I can simplify with a factor from the denominator. So, luckily, wow. So, negative 6 divided by x plus 1 cubed. I really like that. And this is what I see. For the purpose of the studying of the sign. Do I have to do this? No, you can put in the calculator. I know that, but by the time I put in the calculator and I punch in the numbers, I may even make an error. This is much easier for me. Okay, so to the left of negative 1, it's positive, right? To the left of negative 1 is positive. And to the right of negative 1 is negative. Which says this. Okay. One more step. I hope you agree that x squared minus 4 divided by x plus 1. I can use, in this case, the synthetic division to divide. Or I can use the long division. What would you like? Long division? Yes? Okay. So I'm going to divide x squared. They are in descending order. Minus 4 because the middle term is missing. And I divide by x plus 1. And you can say, why are you dividing? In a second, I'll explain. So x times 1 is x squared. X times what is x squared? X. X times x is x squared, we subtract. X times 1 is x, I subtract. Negative x minus 4. X times what is negative x? Negative 1. Negative x plus x, negative 1 plus 1. So the remainder is negative 3. Would you accept if I write this, x minus 1 minus 3 over x plus 1? I claim that the original function, which is x squared minus 4 over x plus 1, is the same with this one. Would you accept? Would you agree? Okay, let's check. X minus 1 times x plus 1 is x squared minus 1, x squared minus 1 minus 3 is x squared minus 4. So I rewrote this. I could have not done that if the degree of the top were smaller. I could have done it when the degrees are the same, but there is no need, because it's a horizontal asymptote. There is no need for that. But here, when the degree of the top is by 1 unit higher than the degree of the denominator, the quotient will always be a line. And this is the slant asymptote. Just this. Why? Because at infinities, this dictates this approaches what at infinities? What will this piece approach when x approaches infinity or negative infinity? We don't care.
0.
Exactly. So this, just the quotient, is the slant asymptote. So back to the table. Y equals x minus 1 slant asymptote. And that's just the quotient. So let me write that for you. The quotient of the division x squared minus 4 over x plus 1 is the slant or oblique asymptote that has to be graphed. I have to graph it like we graphed the vertical asymptotes, the horizontal asymptotes. This has to be graphed. Because when we graph functions with asymptotes, we have to start by graphing the asymptotes first. So, give me 2 points for y equals x minus 1. Of course, when x is 0, how much is y? Negative 1. So 0, negative 1 is this point. And when y is 0, how much is x?
1.
1. So 1 comma 0. So this is y equals x minus 1, the slant asymptote, and it has to be graphed. It's not a solid curve or a line. It's not part of the graph of the function, but it has to be graphed. And also we have x equals negative 1. Only now we're ready to start the graph. That's why we have to do this. We have to find the quotient. Okay, so let's see. From negative infinity, crossing the x-axis at negative 2, 0, going to infinity. Fine. So here's negative 2, 0. From negative infinity, crossing, going to infinity. Fine. From negative infinity, crossing at 0, negative 4. Crossing at 2, 0. From negative infinity, crossing the y-axis at 0, negative 4, the x-axis at 2, 0, and going towards infinity. It has to be asymptotically going to infinity. Approaching, getting closer and closer to the slant asymptote. So this was f of x, x squared minus 4 over x plus 1. So we really mean it. The function has to approach the asymptotes. When it goes to infinity approaching that, when it goes to negative infinity approaching this way. And of course the vertical asymptote. So when you put this in the calculator, just in case you want to do that, I wouldn't waste my time for some of these, but of course you can and you should check just to make sure. Don't forget parentheses around the numerator and the denominator. X squared minus 4 and x plus 1. And you must put the x minus 1 as the second function. The calculator would not graph it. So assuming we use the standard viewing window, I think I used that before. So let's see what we get. Here's the function, and here comes this slant asymptote. And as you see, the function gets closer and closer. We say it approaches asymptotically, no?
Is the slanted asymptote always the opposite sign as the denominator? So like the denominator there is x plus 1.
If you want to say that, it's always the sign of x minus 1 in this case. So the end behavior and the slant asymptote is the same thing with the horizontal. The end behavior is 1 or 2 or whatever. The slant asymptote in this case is x minus 1, so that's why the end behavior must be this. It's the same thing with the horizontal, but functions that have horizontal cannot have slant. Rational functions. Rational functions that have slant cannot have horizontal. A function can cross a horizontal asymptote, and it can cross a slant. But the one that will never ever dare to cross is absolutely. Very good. Now, we'll have other functions to graph if you'd like. If you want to choose other functions, I'll show you where they are. I just would like to look at some L'Hopital's rule. But I know I only have about 20 minutes.
That's a question.
Yes, please.
Where did we find x equals 0, y equals -1, y equals
Oh, when we graph a line, sorry about that. So we have y equals x minus 1. When x is 0, y is -1. The x and y intersect. And when y is 0, you move 1 to the other side, and you get x equals 1, which is 1 comma 0.
Okay.
These are the x and y intercepts needed to graph the slant asymptote.
Okay.
It's a line, so I need the x and y intercepts. When x is 0, I find y. When y is 0, I find x.
Okay.
Sorry about that.
Yeah.
Okay, so of course you can choose. If you'd like to continue with these graphs, I'll be more than happy to show any function you want. Just keep in mind that some of them will take us like 20 minutes. But if not, what I would like to continue with, but it's up to you, I would like to continue with more L'Hopital's rule, limits with L'Hopital's rule. Because we did use it, but there are other indeterminate cases. Remember, there are 7 indeterminate cases. And we only looked at 2 or 3. I need to show you the other indeterminate cases. But if you'd like to choose another function, yes, no?
Can we look at finding another slant asymptote?
Yes,
without,
of
like,
course.
a chart and everything?
Yes, of course. Yes, of course. They are here. Use the guidelines of the section to sketch the curve in guideline, blah, 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 blah. And all these, this has degree 2, degree 1, degree 2, degree 1, degree 3, degree 2, degree 3, degree 2, blah, blah, blah. I don't know. These have exponential, I don't know. I haven't looked at those. So anything that has, find the equation of the slant asymptote, do not sketch the curve. So if you just want to find a slant asymptote, we can do that. So please choose.
64.
We want to look at 64. You just want to find the slant asymptote and not the whole thing? Okay, perfect. Good pick.
When we do the long division to find the slant, the remainder is not needed. It's just
So, very good question. So the slant asymptote is only telling us where does the function go. The slant asymptote has to be a line. It cannot be something x squared or x cubed. It has to be a line. y equals 3x minus 5, or y equals 15x minus 2. But it cannot have any other degree but 1. And it should have, because if it degrees 3 divided by degree 2, we get degree 1. Degree 5 divided by degree 4, we get degree 1, correct? So when x approaches infinity, like let me show with the example that we just had. Very good question. So, of course, that's the only thing I can see. Okay, so we divided this function and we got this, right? The quotient minus the remainder over the divisor. Okay? So now when this will tell us this is the same with the function. It's the same. So now when I find the limit of this as x approaches infinity, I find the limit of this as x approaches infinity. This piece goes to 0 and this piece goes to infinity. When you find when x approaches negative infinity, this piece goes to 0 and this piece goes to negative infinity. And this is the portion that I graph. And that's what tells me where the function is going. If it had a negative in front, it would have been this.
And
But
that's,
it has positive in front, so it's this.
that's why you set it to y equals.
Right. So this is the piece that I graph. This goes to 0. Because remember, we're only talking, when we talk about horizontal asymptote or slant asymptote, we really talk about way there, up there, and way up there, not in the middle. The middle has no meaning. In the middle of the graph, or around the x-axis, the origin. We're talking about way up there and way down there. But we have no choice. I can't graph lines doing this. A little piece here, and a little piece over there. I have to graph the whole thing, right? But in the middle, it means nothing. It's only up here and only here when the function gets closer and closer to it. But I have no choice but graph the whole line. I cannot just show you a little piece over there and a little piece over here. I have to graph the line. Does it make sense? Okay, perfect. We picked, I have no idea. Oh, 64. So we have y equals 5x to the fourth plus x squared plus x, everything divided by x to the third minus x squared and plus 2. Does this function have a slant asymptote? And the answer is yes, only if the degree of the top is exactly by 1 unit higher than the degree of the denominator. Otherwise, the answer is no. So, yes or no?
Yes.
Yes, perfect. So now, I make sure the top and bottom are in descending order. Are they? Because if they're not, I have to rearrange the function. Yes. So the degree of the top is 4. I have 5x to the fourth. I do not have x to the third. I leave some room, x squared and then plus x, and then the free term is also missing. The denominator, there is no need to leave any space there. But the numerator, it has degree 4. Any degree 4 polynomial has to have 5 terms. But this one doesn't. It has degree 4. It does not have degree 3. It has degree 2. It has degree 1, and it's missing degree 0. Degree. This one I don't care, as long as it's in descending order. So now the first question is, this times what is this? Let's write it on the side. X cubed multiplied by what is 5x to the fourth? At the top, we never lie. Yes. Yes. So it's 5x. Remember, the quotient must be a line. Must be a linear function. Degree 1. So now, I go back and distribute. 5x times x to the third is 5x to the fourth, but I have to subtract. 5x times negative x squared is negative 5x cubed, but I have to subtract, and I needed that space. I need this space because I couldn't put 5x cubed under anything else. I have to put it under the term with x cubed that is missing. And finally, 5x times 2 is 10x, and I subtract, and I have to place it in the correct spot. Be careful. So 5x times x cubed is negative, it's 5x to the fourth, subtract. 5x times a negative x squared is negative 5x cubed, subtract. 5x times 2 is 10x, subtract. But it has to be under x. Placed under like term. Gone, 5x to the third plus x squared minus 9x. Final question, and it has to be final, because I'm expecting the line. X cubed times what is 5x cubed? Yes, and the side, I need the sign. Plus 5. So positive 5x cubed, negative 5x cubed, negative 5x squared, positive 5x squared, and positive 10, negative 10 completely outside, gone, 6x squared minus 9x minus 10. Okay, it was not a friendly situation, but here's how we write the function now. Can anyone get us started? Very good, awesome. Plus, I have to write a symbol, all this remainder, 6x squared minus 9x minus 10, everything over x cubed minus x squared plus 2. So if I find the limit from the original function or the limit from this function when x approaches infinity or negative infinity, what will I get? When x approaches infinity, I get infinity because that goes to, of course, much bigger in the denominator, eventually will go to 0. You can use L'Hopital's rule, you're going to get 0. And when x approaches negative infinity, this goes to negative infinity because that piece goes to 0. Any questions about the slant asymptote? So if you graph this function, no, you're not going to get something like this. No. Just the first derivative will take us 10 minutes. No. That defies the purpose, right? So, so when you graph this function, you're going to have to graph 5x plus 5. That would be the slant asymptote. It happens to have a positive slope, so we know it will eventually, the function will eventually follow it, get asymptotically closer and closer to it. Very good. Any questions? Okay, we have 9 minutes left. What would you like to do? Would you like to look at a couple of L'Hopital's rule, easy ones? Is that a yes?
Yes.
Okay. In that case, allow me to choose. So I can choose easier ones. So one more time, let me show you where we are. So this is section 4.4. We already have knowledge of the L'Hopital's rule, but not the sophisticated type of problems that we're going to look at. 4.5 is done because we already used everything from 4.5. 4.6, you're not going to be tested on because we are doing calculator work. We have 2 more sections left, which is optimization 4.7 and Newton's method 4.8. So after we finish L'Hopital's rule, we have 2 more sections. And then we'll start reviewing. Okay. On page 308, okay, so let's start with 30. So we have limit as x approaches infinity from natural log x squared divided by x. I will apply L'Hopital's rule if it's applicable. So first I have to plug it in, and when I plug it in, I get what? Good. So L'Hopital's rule is applicable. So then I have limit as x approaches infinity. What do I get at the top? Remember, we have to use the chain rule because we have a function that is squared. So we get 2 times natural log x times, yes, very good, Andre, thank you, over 1. Perfect. So this is limit as x approaches infinity from 2 natural log x divided by x. If this happens to be infinity over infinity or 0 over 0, I can continue. I plug it in, what do I get? So then limit as x approaches infinity, the top is times 1 over x. The denominator is 1. So finally we have limit as x approaches infinity from 2 over x, which is perfect. I don't think you would have expected that. Uh, 21, something that we struggled with a long time ago. 21 on 308. Limit as t approaches 1 from t to the 8th minus 1 over t to the 5th minus 1. Not knowing or not having as a tool L'Hopital's rule, the only option would have been to factor. You don't want to factor either one. I mean, the top is okay, but okay. So when we plug in 1, what do we get? Right, and that's nice because 0 over 0 or infinity over infinity, we can use L'Hopital's rule. So then, limit as t approaches 1 from the numerator, which is
7.
very good, and 5 to the 4th, very good. So I'm going to simplify and get t to the 3rd at the top. And now we plug it back in again and we get very good. Not too difficult. Questions? $25. Any questions? Is this okay? 25. Limit as x approaches 0 from e to the x minus 1 minus x, everything divided by x squared. Let's see what this is. I'm hoping for 0 over 0 or infinity over infinity.
Yeah.
Which one?
0.
Very good. It is indeed 0 over 0. So then I have limit as x approaches 0. The top is, remember we can never divide like this unless it's a limit which turns into 0 over 0, infinity over infinity. We never divide, we never differentiate a ratio like that unless it's a function inside a limit and the requirement is 0 over 0 or infinity over infinity. So the top is e to the x minus 1 and the denominator is 2x. Okay, we try again. If it's still 0 over 0 or infinity over infinity, I can apply L'Hopital's rule again.
0.
It is 0 over 0 indeed. So then limit as x approaches 0, the top, e to the x, yes, divided by 2, so it's indeed 1/2. Very good. Okay, just one more and I promise to stop. We did not get to the sophisticated ones. We're still looking at those two simple ones of 0 over 0 or infinity over infinity. So next time we'll look at the complicated ones. Yes. Let's look at 33. Limit as x approaches 0 from x plus sine x over x plus cosine x. I hope again for 0 over 0. The denominator is 0. Yes, this approaches 1, and the numerator is 0 plus 0. So the numerator is 0, and the denominator is 1. So the answer is, I did not have to use anything. That's why it's mandatory to plug it in first, because you can